So in this lecture, we will discuss about sorting algorithms. Sorting refers to the operation of arranging data in some order, such as increasing or decreasing with numerical data or alphabetically with character data. So if the data is numerical, either increasing order or decreasing order, or if the data is alphabets, or then you have to sort alphabetically. So complexity of sorting algorithm. Each sorting algorithm will be made up of the following operations. These are basic operations, in fact: comparisons, interchange, and assignments. So we will be discussing several sorting algorithms, several standard sorting algorithms, and the basic operation in those standard sorting algorithms are these three. Comparison, that is when you compare two numbers or two words, okay, to check whether the first number is smaller or larger. Second operation is interchange, okay, that is you will be swapping the two numbers or words if they are not in the proper order. It's called swap or interchange. And the third operation is assignment, okay, so putting the value of one number into another. So you will be using these three basic operations in the sorting algorithms. Okay, sorting algorithms can be divided into these two categories: internal sort and external sort. So an internal sort is an algorithm which uses main memory exclusively during the sorting operation. Okay, so it means that your entire data, for example, you are sorting the numbers which are stored in an array. Okay, so the data structure is the array, and you are sorting all the elements stored in the array. So internal sort is that algorithm which assumes that the entire array is in the main memory. Okay, so since the main memory is high speed random access memory, so internal sorts are faster than external sort. And external sorts also uses external memory. Okay, external memory means either the tape drives or the disk drive, hard disks, during the sorting operation. Okay, that is, during the sorting operations, data may be copied from the hard disk into the main memory or copied back from the main memory to the hard disk. Okay, so if the sorting algorithm also include these operations, that is movement of data from between the main memory and the secondary storage devices like tape drives or the disk drives, then the algorithm is called external sorting algorithm. Okay, and external sorting algorithms are usually used with large database files when your file cannot be entirely stored in the main memory. So in that case, what will happen? You will bring some part of your large file into the main memory, and then you will sort that part. Okay, and then you will write that sorted part back to the hard disk. Then you will move the unsorted part of your file into the main memory. You will sort that unsorted part and then move back to the hard disk, and then using some merging technique, those sorted parts which are now on the hard disk are combined in the main memory. Okay, so uh, that is called the external sorting algorithm, which sorts very large files which cannot be entirely stored in the main memory. So in this course, we are concerned only with the internal sorting algorithm. Okay, external sorting algorithm are usually used with large database files. So you will study the external sorting algorithm in the database course. Okay, so we will start by bubble sort. We will first discuss bubble sort, the oldest and the simplest sorting algorithm, and it is also the slowest sorting algorithm. That is, the order of complexity of the bubble sort is worst. Okay, so general idea of the bubble sort algorithm is this. That is, you compare each item in the list or array with the item next to it and swapping them if they are not in the proper order. Okay, so proper order means if you are sorting in the ascending order, okay, then you see that the first number is greater than the next number, you will swap them. Okay, and vice versa. Okay, so for example, you are swapping the items in increasing order. Okay, so when you so consider this very small list having only three elements, a1, a2 and a3. So what will do, you will compare each item in the list with the next item to it. So you will compare a1 with the next item, which is the a2. So if you found that a1, remember we are sorting in ascending order. Okay, so if a1 is larger than a2, you will swap them. Okay, then you will, okay, so let's assume that we have swapped them because a1 was larger than a2. Now you will compare a1 with a3. If a1 is also larger than a3, you will again swap them. Okay, so now the final list will be a1, a2, sorry, a2, a3 and a1. Okay, so now this is called one pass of the bubble sort. Okay, one step or one pass of the bubble sort. So after the first pass, you will see that you have the largest element in the list or array is at the last position of the array. So the largest element in the array will be at the last location after you have finished the first pass. Okay, the same process will be applied on the subarray starting from the index 1 goes up to the second last index n minus 1, because you have already got the largest element at the last location. Okay, so now you will apply the next pass, the second pass on the subarray. Okay, and the indexes of the subarray will start from 1 and goes up to n minus 1, and after the second pass you will have the second largest element at the index n minus 2, that is at this location. Okay, and then the same process will be repeated in the third pass, and at the third pass you will have the third largest element at location number index number n minus 2. Okay, so this process is repeated until the entire list is sorted. Okay, so in this way you can see that in each pass the largest element is moved up to its proper position or is moved towards the end of the list. Okay, so this is called bubbling up towards the end of the list. That is, the largest element is bubble up to the end of your subarray. Okay, so that's why this algorithm is known as bubble sort, because the largest element in the subarray is bubble up to the end of the list, to the end of the subarray. Okay, now the bubble sort algorithm in more finer detail. Okay, suppose you have an array A. Okay, and the index of the array start from 1 goes up to n. The size of array is n. Okay, so entire array is in memory. It means that the bubble sort is an internal sorting algorithm. Okay, so this is the first pass of the bubble sort. Compare a1 with a2, arrange them in the desired order. Okay, so that a1 is less than a2. Okay, and this is for the ascending order. Okay, so compare a1 and a2. If a1 is greater than a2, then interchange them, swap them. Okay, then compare a2 with a3. Okay, if they are not in proper order, then arrange them in proper order, and so on. And This will be repeated until you have compared the last two elements in the array. That is, in the last of the first pass, you will be comparing an minus 1 with an. So if these two elements are not in proper order, you will interchange them. So this is the first pass of the bubble sort algorithm. And after the first pass, at the last location, you will get the largest element of the entire array. Okay. So after the first pass, uh, the largest element is at its proper position at the last location. Okay, but the subarray from index 1 to index n minus 1, okay, this subarray is not sorted. So what we will do in the second part, we will consider only the subarray from index 1 to index n minus 1, and the same process will be repeated. That is, a1 will be compared with a2, then a2 will be compared with a3, and so on. And in the last, an minus 2 will be compared with an minus 1. Okay, and if they are not in the proper order, an interchange operation will take place. And after the second pass, you will also have the second largest element at index n minus 1. Okay, that is, after the second pass, the last two elements are at its proper position. Okay, and the subarray starting from the index 1 up to index n minus 2 are not sorted. So in the third pass, you will sort that subarray from index 1 to index n minus 2. Okay, so in this way, how many passes you will have? You will have n minus 1 passes. Okay, and in the n minus 1 pass, you will be comparing a1 and a2. Okay, in the subarray, we will have only two elements, a1 and a2. Okay, so you will compare a1 with a2 and arrange them in proper order. Okay, and after that, you all the largest n minus 1 elements will be at their proper position, and the subarray you will have only one element. Okay, and that element will be the smallest element, so there is no need to have the nth pass. Okay, so only n minus 1 steps or n minus 1 passes are sufficient to sort the all the numbers, all the elements in the array. Okay, so total number of passes or total number of steps in the bubble sort is n minus 1. Now see the example. So this is your array A, and the size of the array is 1, 2, 3, 4, 5, 6. Size is 6. That is, index starts from 1 and goes up to 6. Okay, so in the first pass, you compare A1 with A2 initially. So A1 is 6, A2 is 5. So compare them. 6 is greater than 5, and assume that you are sorting array A in ascending order. Okay, so A1 must be smaller than A2. So an interchange operation will take place. Okay, so you will interchange them. Okay, 5 will be stored at A1 and 6 will be stored at A2. So swap operation or interchange operation take place. Now you compare A2 with A3. Okay, A2 6, A3 4. So another swap operation will take place. Okay, swap 4 and 6. Then compare A3, A4. Okay, 6 is greater than 3, so another swap. Then compare 6 and 2. Okay, 6 is greater than 2, so swap them. Then compare 6 with 1, 6 is greater than 1, again swap them. Okay, so this finishes the first pass. Okay, and after the first pass, the largest element in the array is bubble up or sent to the end of the list. Okay, so in some literature it is called bubble down to the bottom of the list. On some literature it is called bubble up to the list, bubble up to the end of the list. Anyway, it is the bubble. So bubble up or bubble down. So bubble sort algorithm. So this finishes the first pass. Now this subarray is not sorted. The largest element is at at its proper position, but this subarray is not sorted. So the same process is repeated again, but only for this unsorted subarray from index 1 to index n minus 1. Okay, so again you will start comparing with a1 and a2. So 5 is greater than 4, so swap will take place. Then compare 5 with 3, another swap will take place. Compare 5 and 2, swapping operation will also take place. Compare 5 with 1, another swap. So this finishes the pass number 2. So the last two elements are sorted, but this subarray is not sorted. Okay, so third step or third pass will also be required. Okay, so compare 4 and 3. 4 is larger than 3, swap them. Okay, then swap 2 and 4, also swap 4 and 1, and this finishes pass number 3. Okay, so this subarray is not sorted yet. So again run the next pass, compare 3 and 2, swap will take place. Okay, compare 3 and 1, another swap. Okay, the fourth pass is complete. Last 4 elements are sorted. Fifth pass, compare 2 and 1, swap them. Okay, and this was the last pass. Okay, if there are n elements, the total number of passes n minus 1. So in this case we have 6 elements, so number of passes 6 minus 1, 5. Okay, so after the execution of the bubble sort, after the execution of 5 passes, the array is sorted. Okay, so now you see in a pass how many comparisons are required. Okay, for example, in the second pass, you go to the second pass. Yeah, this is the end of the first pass. Okay, and this is the beginning of the second pass. Okay, you will compare these two elements, then these two elements are compared, then these two elements are compared, and then these two elements are compared. So 1, 2, 3, 4. Okay, so 4 comparisons, and this is the second pass. Okay, and in the first pass, 1, 2, 3, 4, 5. Okay, so you can see that in the first pass 5 comparisons are required, in the second pass 4 comparisons, and you will see in that in the third pass 3 comparisons, and the fourth 2, and the fifth pass only 1 comparison is required. That is, you compare only a1 and a2 in the last pass, in the fifth pass. Okay, so it means that in the kth pass, where k lies between 1 and n minus 1, the number of comparisons will be n minus k. Here, in this particular case, the value of n is 6. So you can see that this is the value of k, and n is 6. So when k is 1, number of comparisons 6 minus 1, 5. When k is 2, number of comparisons 6 minus 2, 4. When k is 4, number of comparisons 6 minus 4, 2. Okay, so in general case, in the kth pass, the number of comparisons will be n minus k. Okay, so in the bubble sort algorithm, there will be total n minus 1 passes, and in the kth pass, you will have to compare n minus k times. You will be comparing elements n minus k times. Okay, so now we will try to write the algorithm for the bubble sort, and after that we will find the complexity of the bubble sort. Okay, so this is the bubble sort algorithm. So here data is the array, size is n. Okay, so this is the first part of algorithm and this is the second part. Okay, there are four steps. Step 1, 2, and this is step 4, not 1. Okay, so there are n minus 1 passes. So you have a loop, repeat for loop, repeat step 2 and step 3 for k counter starting from 1 to n minus 1. So n minus 1 passes. So step 2 and step 3 will be repeated for each pass. Okay, set pointer variable, a temporary variable, ptr is equal to 1. Okay, step 3, repeat while. Repeat while ptr is less than equal to n minus k, because you have to compare elements n minus k times in each pass. Okay, so ptr starts from 1 and goes up to n minus 1. This is less than or equal to. Okay, so starts from 1 and goes up to n minus k. So data ptr. Okay, so initial value of ptr is 1. So data ptr is compared with data ptr plus 1. That is, you will be comparing a1 with a2, data 1 with data 2. Okay, so if data ptr is larger than data ptr plus 1, okay, this is for the ascending order. Okay, so you will interchange data ptr and data ptr plus 1. Okay, and after interchanging them, you will increase the value of ptr variable. Okay, so this will be repeated n minus k times. Okay, and after finishing both the loops, both the inner and the outer loop, the algorithm exits. Okay, now try to find the complexity of the bubble sort algorithm. Okay, you can see that the complexity of the bubble sort algorithm is same for all the three cases, for the best case, for the worst case, and for the average case. Okay, because the algorithm does not depend on the values of your array. Okay, no value in each pass, the number of passes is fixed n minus 1, and each pass number of comparison is also fixed. Number of comparison in each pass does not depend the actual values of the array. It is fixed for each pass. Number of comparison is fixed n minus 1. Number of comparison in each pass is also fixed n minus k. Okay, so even if you give a sorted array to the bubble sort algorithm, it will require n minus 1 passes, and each pass and in the kth pass it require n minus k comparisons. Okay, so it doesn't matter whether you are giving a sorted array to the bubble sort or you are giving a completely unsorted array to the bubble sort, the number of comparisons will be same in each case. Okay, so both that is for all the three cases, for the best, worst, and average case, the complexity is same. Okay, and you can easily find the complexity. Try to find the number of comparisons. Okay, remember that there are three basic operations. You can count, interchange, assignment, and the comparison. Okay, so in the bubble sort algorithm, there are some assignment statements which requires constant amount of time, and there are some comparisons. This is comparison, this is also comparison. Okay, and there is also interchange. Okay, so this interchange depends on this condition. Okay, if this is true, then interchange will take place, otherwise it will not take place. Okay, so you can see that the number of interchange operation is always less than or equal to the number of this comparison. Okay, so it is always less than or equal to, so you can approximate it by only this comparison, because it is always less than or equal to. So instead of finding both the interchange and the comparison operation, we just count the number of comparisons. because it is fixed. It can be found easily. So in the first pass, how many comparisons will be there? One, sorry, n minus 1 comparison. In the second pass, n minus 2 comparison. Third pass, n minus 3 comparison. Okay. Kth pass, n minus k comparison. And in the last pass, which is the n minus 1th pass, n minus n plus 1, that is only one comparison. So this is statement. Okay, so 1 plus 2 plus 3 up to n minus 1. So this is equal to n into n minus 1 by 2. Okay, so it can be written as n square by 2 minus n by 2. Okay, so to find the order of complexity, what you do, you take only the higher order term, that is all the lower order terms are neglected, and all the constant are also neglected, and you find the order of complexity as big O of n square. So this is the complexity of bubble sort algorithm in all the three cases: best case, worst case, and average case. Okay, now there are some variation of bubble sort which performs better than the standard bubble sort algorithm. The order of complexity of these variation remains same, order of n square, but the number of actual comparisons might be lower than the number of comparison in the standard bubble sort. So in other words, you can say that the in big O notation, the complexity remains same, order of n square, but the running time complexity of the variation of the bubble sort is smaller than the running time complexity of the standard bubble sort. The actual number of comparisons are smaller, but the order of complexity is remains same, order of n square. Okay, so the first variation is called bubble sort with early termination. Okay, so in the bubble sort, you see that the number of passes is n minus 1, even if the given array is already sorted. Okay, you can easily check if the array is already sorted or not in this inner loop of the bubble sort. Okay, so if no interchange takes place during the execution of a pass, it means that the array has been sorted or already sorted. Okay, so you can easily check if an interchange operation has taken place in the inner loop or not. So for this purpose, you can declare a boolean variable flag which is initialized to false, okay, before the execution of each pass in the outer loop. Okay, and if no interchange operation take place, the value of flag remains false, and if some interchange operation, at least one interchange operation take place, then value of flag is set to true. Okay, so after the execution of the inner loop in the in each pass, you check the value of flag. If the value of flag is true, it means that an interchange operation has taken place. It means that array is not sorted yet, possibly not sorted yet, so you will go for the next pass. Okay, and if the value of the flag is false, it means that no interchange operation has taken place in this pass. It means that the array is sorted, so there is no need to go for the next pass, and you can stop your bubble sort algorithm. Okay, so in this way, the number of passes in the bubble sort can be reduced. The number of passes will be less than n minus 1. Okay, and it depends on the actual data. Okay, if now in the best case, if the array is already sorted completely, only one pass will be required. Okay, and in the worst case, if the array is sorted in reverse order. Okay, now second variation of the bubble sort. Okay, in the second variation, uh, you sort the array in opposite direction in alternate passes. Okay, so in the standard bubble sort algorithm, you bubble up the largest element towards the end of the list. Okay, in this variation, alternate passes in opposite direction, in one pass you bubble up the largest element towards the end of the list, and in the next pass you bubble down the smallest elements towards the beginning of the list. Okay, so for example, say in the pass 1 you bubble up the largest element towards the end of the list, and then in the second pass you bubble down the smallest element towards the beginning of the list, and then in the third you bubble up the largest element towards the end of the list, towards the end of the subarray, in fact, and then in the fourth pass you bubble down the smallest array towards the beginning of the subarray, and this continues uh, until the n minus 1 pass. Or if you are using with you are also using the early termination method, so this will continue until your array is sorted. Okay, so this also reduces the number of comparisons. Okay, in fact this may reduce the number of comparisons. It is not guaranteed, it again depends on the actual data, but for most of the data the number of comparisons will reduce if you use alternate passes in opposite direction variation. Okay, so these are two variation of the bubble sort which reduces the number of comparisons, but it does not reduce the order of it does not improve the order of complexity. Order of complexity remains same, order of n square in all the three cases. Order of n square in best case, order of n square in fact I should say it remains same for the average case and the worst case, because in the best case it will reduce to order of n if you are using early termination. Okay, because if the array is already sorted, so only one pass will be required, and in the first pass there will be only n minus 1 comparison, so neglect the constant, complexity will be order of n. Okay, so it means that bubble sort with early termination has order of complexity, order of n square in both worst case and average case, but in the best case the order of complexity is order of n. Similarly, in alternate passes in opposite direction, okay, if this is combined with early termination, again the best complexity will come out to be order of n, but in the average and worst case it will be order of n square.